Now we're going to see a couple of demos here. And I think you'll find a common theme in multi-dimensional analysis. So the oceans and the atmosphere are obviously dynamic systems. They do different things at different times. And traditionally in GIS, we've only been able to do one depth slice at a time or one time period at a time. And so the commitment that we're making is to tackle both of those in the same work. So Keith Van Graffelen is going to show us our first example using data from the Living Atlas as well as the Ecological Marine Units. And Keith's going to focus on some localization workflows for the Ecological Marine Units. So take it away, Keith.
Thanks, Drew. Thanks, everyone, for being here. Excited to share with you guys the ability to, for everyone to make local ecological marine units. So for those of us not familiar with ecological marine units, the goal is to maintain a healthy ocean and support sustainability. It's necessary to have a baseline for understanding the ocean's ecosystems and a framework for detecting change. Ecological marine units are global, 3D, long-term mapped ecosystems that can help meet these goals. However, they are sometimes too temporally or spatially coarse to be used in bays, estuaries, or nearshore waters. So you can leverage the workflow used to create global EMUs to build, visualize, analyze, and share highly localized EMUs using data from both the NOAA's World Ocean Database and your local in situ observations. So here's the problem, right? So here we're looking at a 1 by 1 degree area off the west coast of Hawaii, and we've got 16 different vertical cylinders that comprise 9 different EMU types within this 1 by 1 degree area. And what we want to do is we've got some better observational data that we want to really have a denser grid that we can work with and interpolate with our own information. So here is the workflow. Once it's followed, you're able to generate this much denser, much more localized 3D point mesh that has much more observations associated with it. So here we're looking at around 164,000 points over 1,280 different vertical cylinders. So much more, much denser than the global EMU work. So how did we do this? So we follow this very easy workflow to get there. So here is the actual workflow that we used for the local EMU clusters, and I'm going to walk through this quickly. So in the case, we started with good data from NOAA. We were able to go to the NOAA Select site and obtain netCDF files of temperature, oxygen, and salinity. And then this is where the GIS comes into play. So I've got these netCDF multidimensional files that are out there, and what we're going to do is we're going to convert that information into this feature class, ultimately, that we can start to work with in GIS. So along the way, we have a couple steps to get there, and that really is importing the data, making an event layer, and getting in that Esri tedious time format, right, that we need to have our data in. So getting that really set up and structured properly, and getting your coordinate system defined. So we're going to be doing some interpolation. It's going to be important to have a projected coordinate system in this case. So that's the first task of getting your data loaded into GIS. And then beyond that, we want to explore the data, and that's where the generate charts, summarize, and symbolize comes into place. We've imported this massive data, and we need to familiarize ourselves with it rapidly and get a better understanding of what we're dealing with. So that's what the second task focuses on. The third one is generating a 3D point mesh, and the information gathered from the previous step will help us do that. And once we have that regularly spaced point mesh and we've got our observational data, we're able to start our interpolation. And we've got different methods to do that. And from there, we can do visualization, summary plots, and tables, and we've essentially created our local EMUs at that point in time. So we've simplified that crazy workflow into these 5 tasks in ArcGIS Pro. So these tasks are pre-configured steps that guide a workflow or a business process. They can be used to implement best practices or improve the efficiencies. You can tweak these if needed. Tasks provide a repeatable and reproducible product. So that's very important here if we're going to iterate through some of these different tasks. So the 5 tasks can simply be broken down into converting your data, visualizing and summarizing your data, building that mesh, interpolating to it, and clustering. So here we're going to take a look at task 1, where we have really that bulk load of the information coming from that data that we downloaded and ingesting it into a file geodatabase. So here we can see that we've got a GUI that pops up on the right-hand side that leads us through a task, and it asks us what our variables are that we're working with. In this case, we're working with temperature, and we're defining our coordinate system as well that we're going to be working with. So in the case of Hawaii, we're using UTM Zone 5 North. Once we have the data input, so as you can see here, the data for temperature, it's been symbolized and it's added to the map. And we can see that there's kind of a randomness of these observations that are all over the place. And we can get an understanding of the data. It's a good start. What's next is to visualize and summarize the charts. And we're able to run another task, which is task 2. And you say, here's my temperature layer, and it generates these charts for you. And these 3 charts are a scatter plot of temperature by depth. So here's that same color pattern that we symbolize the data by in the map inside this graph. And you can interact with this graph and select the features in this graph, and it selects them within the map as well. There's also a histogram of the temperature values. So here I can quickly get an understanding of most of my data values are between 0 and 32 degrees Celsius. So that's good information. I know the mean, the median, and the standard deviation. And I also can look at the extensive record of observations associated with temperature. So this data actually goes back to, there's observations dating back to 1929 for this area that we downloaded from NOAA Select. But I do have much more information that's within the past 30 years. So this chart here might inform me to use the last 25 or 30 years of recent measurements and maybe remove some of the older measurements if I choose to do so. So these are information products that help guide you along the way to make those decisions about how you're going to construct your local EMUs. So the next step here is actually within task 2, there's 2 steps, and this is step 2, is explore the point spacing. This gives you an idea of what your average 2D and 3D distance is between the observations that you've just brought in. So this will play an important role in how we specify the distance, the spacing of our 3D mesh that we're going to generate in the next step. So instead of flying blindly and doing some measurements, this provides you with some good guidance that you can choose to use or not when you go to create your 3D mesh. And that brings us to the third task here, where it really asks us about, how we're going to build the mesh. So we're going to specify our study area extent. It's typically going to be the same extent as the temperature features that I just brought in. We're going to pick our horizontal cell size. So this is where that information from the previous geoprocessing task can be informative. And we're going to choose our depth levels. In this case, we went with World Ocean Atlas Standard. And here's where you have the ability to incorporate a bathymetry layer. So think about creating this grid. It needs to know where to stop, where the bottom is. So this bathymetry layer informs that grid of where the bottom is, and it cuts off those regularly spaced points at the bottom, so you have that continuity with the seafloor. And this is run, and we've got these regularly spaced aisles, right, of local EMUs that you can see here on the screen after that's ran. Now we've got the grid, and we've got our observational data inside of our project. We're ready to interpolate at this point. So here we walk through task 4, and we can look at the temperature feature class again. We can specify the target feature class, so we're going to be writing these observational data and interpolating to our mesh. And we have an option of an interpolation method. So we have 2 options within these tools right now. And you have nearest neighbor or you have linear. And once that happens, I have populated my attribute table with the temperature recordings. And at each one of those points for these EMUs, I have a temperature value that's been interpolated. So here's an overview of that tool and the different options for interpolation and the linear method described. Once you have the attributes available to you, task 5 lets you cluster. So whatever information you've interpolated to your point mesh at this point in time, you have the ability to look and cluster and see if there's patterns within your data to where it can be grouped together to say that these water masses are similar to these water masses because of these characteristics. So that is what is going on with the clustering. And in this case, we specified just temperature, the one variable, to see what we came up with as far as clusters. And we were informed that by that task running, that the optimal number of groups, optimal number of clusters is 30. So it came up with that. It gave us a mean, a standard deviation, a min, a max, and an R-squared value to help validate that. But it also creates a chart to help explore and validate the results of the analysis. And it tells us that right there in the results. So we can get an understanding a little bit more about what those results are by exploring this chart that was created. So let's look at why it generated 30, or why it chose 30. And we could see here that based upon the pseudo-F statistic, that it continued to rise, and why it chose 30. But we also see a change around 16 that might be useful in this case. So we can go back and input this number of clusters as 16 if we wanted to rerun it. So this information is very useful to understand why the number of 30 clusters was come up with, and if you wanted to rerun a result, this is also useful for that as well. So you end up with an attribute table with different clusters that you can then use to symbolize your data and understand if those patterns are there or not. As I mentioned, this is all available for you right now to go and access. So this is available as a pro project. You can go to this URL, and we've included 3 sets of data to get started. So Hawaii, Santa Barbara, and the Western Gulf of Mexico. They're different sizes, areas. Some have more observations than others. We've included temperature, oxygen, and salinity for each. And in certain cases where there's a NOAA coastal relief model, I've included that as well to where you can use that as your bathymetry layer. And if you don't want to use that data, you can go download your own data from NOAA Select for your area of interest and try the workflow on that. Or you can use your own data, right? Jump in at task 2. If you maintain a database of observations, you can skip task 1 and jump in at task 2 and create these local ecological marine units with your own data. So with that, if you recall, I was using a simple form of interpolation for this local EMU method. We had linear and nearest neighbor. While this method is commonly used, there are definitely more sophisticated interpolation methods that can better capture the dynamic nature of the oceans. So Eric Kraus from the Geostatistical Analyst team will preview some new functionality for 3D interpolation.